Hello and welcome. I'm going to talk about our paper cut equivalent trees are optimal for mean cut queries. My name is Ohad Trabelsi, and this is joint work with Amir Abboud and Krauthgamer. So the topic of this lecture is the all pairs max flow problem, or the all pairs mean cut problem. In this problem, we're given a graph, and we need to output for every pair of nodes the maximum flow that can be shipped between them. Now we are going to deal with the data structure and the static versions of this problem. Now, just as a reminder, if we restrict ourselves to a single pair, then the maximum flow and the minimum cut problems are the same. They are practically the same. They have the same value by the max flow mean cut theorem. The current upper bound, best upper bound for the single pair version is m squared 10, where n is the number of nodes and m is the number of edges. Many people in the community actually believe that this problem can be solved in near linear time. It's worth noting that there are faster algorithms in special cases. Now, the naive approach to solve this problem would be to apply a single pair max flow algorithm for each pair, ending up in an n squared applications of max flow running time. Now, 60 years ago, there was a breakthrough by Gomory-Hu that showed how to reduce this problem to trees. Now, what they showed is that is how to construct a data structure of linear size that can answer minimum cut queries quickly. And in fact, they showed something stronger. They showed that this data structure is actually a tree on the same set of nodes as the given graph. So that the minimum SD cut in the tree is also a minimum SD cut in the graph. This tree nowadays is called the Gomory-Hu tree or cut equivalent tree. We can already see that there could be at most n-1 answers. Now, this solution, the cut equivalent trees, are a great solution because they have O tilde of 1 query time and linear space complexity. They're very elegant. But what about the construction time of these trees? So in the general case, Gomory-Hu showed an algorithm to construct those trees in n-1 applications of maximum flow, single pair. And there are some faster algorithms in special cases, in particular for unit capacity graphs. So the main question is it possible to construct cut equivalent trees faster than n applications of maximum flow? Or is it possible to get another data structure with maybe faster pre-processing? So the question is whether these two questions are in fact the same. So now let's talk about some lower bounds. So in the directed case, there could be n squared answers, and no known algorithm can compute the all pairs max flow faster than the naive approach of solving it separately to on each pair. Now, I'll say that if we consider the single pair version, so the directed and the undirected cases are equivalent, and this is proved via folklore reduction. But it holds only for the exact and single pair setting. Now, conditional lower bounds do exist. So for the single source version, where we're given a source and we need to output the maximum flow to every other node, we know that this problem requires n squared time, unless the 3OV conjecture is false, which is the orthogonal vectors conjecture for 3 sets. In particular, set is false, the CTH. Now, assuming the same conjecture, we have also conditional lower bounds, for the all pairs max flow version. we say that it cannot be solved in faster than n³ time, unless the theory of conjecture is false. And we also have a conditional lower bound for dense graphs for the old first max flow version, which states that unless the 4-click conjecture is false, this problem requires n to the omega plus 1, where omega is the fast matrix multiplication exponent. The fourth 4-click conjecture states that one has to put n to the omega plus 1 time in order to find 4 clicks in a graph. And there is also an algorithm with this running time. So back to our questions, these conditional lower bounds don't tell us anything about those questions because they deal with other graph families, the directed graphs, and we deal with the undirected graphs. So are these two questions the same? One direction is simple. So if one wants to construct an all pairs mean-cut data structure and they're given a cut-equivalent tree, it is possible to construct this data structure. And the way to do that is using two-dimensional range queries. This is also something that we show in our paper. It's very simple. But the other direction looks difficult. In the other direction, we need to construct cut-equivalent tree, and we're given a mean-cut data structure. Now, it looks difficult because, for example, for bounded trivial graphs, there exists a mean-cut data structure, but nobody knows how to construct a cut-equivalent tree for this graph family. Another reason that it looks difficult is that in many other problems, trees are not necessarily the best solution. You can think about spawners, for example. So our first result is that yes, these two questions are the same. The cut-equivalent tree can be constructed fast in near linear time, if and only if there is a mean-cut data structure with near linear preprocessing time and polylogarithmic amortized query time. Now this result holds even if the queries are restricted to a fixed source, the queries of the data structure. Now, this shows that it doesn't matter which solution you would come up with for the data structure version. It doesn't matter how crazy it is. I can take it and turn it into a cut-equivalent tree. So that's why it's very significant. Corollaries of this theorem is that cut-equivalent trees can be constructed in near linear time for bounded trivial graphs. And to that we used mean-cut data structure from '98, and this was not known before. We have a similar result for planar graphs, but this was known before, however, using different techniques. Okay, so far I gave you the introduction to the topic and the theorem. Now let me tell you a little bit about the way we prove it. And later I'll show you another result that we have about approximation algorithm. So consider the following map. This is the way we show the equivalence. So first, the reduction between the single source and the all pairs version is trivial. And then the reduction between the all pairs and the cut equivalent tree construction is the simple reduction I described earlier, using the two-dimensional range query. Now, this reduction between cut equivalent tree and the single source and cut data structure is the main contribution of this paper. And we'll focus on that. So now let me describe the Gomory-Hu algorithm quickly. The Gomory-Hu algorithm, we can think about it as running in two processes. We can think about them independently, even though they're not. So in one process, T is a single supernode that is associated with the entire node set. This is the way it starts. And the execution maintains this invariant that T is a tree. And at every iteration, a supernode is being picked and then being split into two, and the subtrees that were connected to I, the supernode, now are now connected to either side of the new to either one of the new supernodes, and so on. We continue, begin a supernode, split it into two, reconnection, etc. Continue until every supernode is a singleton, and then we have the category tree. Now the second process is actually the way we split. How do we split every supernode, and how do we reconnect the adjacent subtrees? So the way we do that is, well, now we pick a supernode I, and then we construct an auxiliary graph from G. So we use the information from the tree in order to construct an auxiliary graph from G. How do we do that? So for every subtree that is adjacent to I, we consider all of the nodes in this subtree and we contract them in G. In this case, we will have 3 contracted nodes. And yeah, this is the auxiliary graph of I. Now we pick a pair of nodes S and T from I, and we compute the minimum cut between them in the auxiliary graph. This implies a partition of the supernode I into 2. One part contains S and the other one contains T. And it also implies a way to reconnect the subtrees. Yeah, so now we're ready to describe the algorithm. So first we perturb the edge weights, and this will guarantee that there will be a single cut equivalent tree with n minus 1 distinct weights. Then we pick a pivot node P, uniformly at random. Note that picking a random pivot was used before. But we use the property as follows. So with high probability, P will have many nodes, at least n over 4, and nodes U, whose minimum PU cut satisfies that their side is smaller than the other side. So the side of U is smaller than n over 2. And this will allow us to have a recursive algorithm. Now, the way we prove that there exist many pivot nodes, so that a uniformly random one will satisfy this property, is by constructing a tournament on the input set of nodes in the following way. For every pair of nodes P and U, we have a directed edge from P to U if in the minimum cut between them, the side of U is smaller than the side of P. Now it is known that in tournaments there exist n over 2 nodes whose out degree is at least n over 4. And this is how we get this property. Now, so let's assume we have a good pivot, one with this property. And then at each iteration, we query minimum PU cuts to multiple nodes U, and then we pick just one of them to progress with. What we show is that indeed one of them will allow us to make a big enough progress in the algorithm. Then when we have this cut, we incorporate it into the tree that is being constructed. We know that this cut does not cross any of the previous cuts, so we can in fact incorporate it into the tree. And eventually we'll have a tree that reflects all of the cuts from P. Now we continue recursively on every one of the supernodes to have a cut equivalent tree for the entire graph. Now visually it looks like that. So we have a supernode that contains the pivot, and then we pick multiple nodes, and then U is going to be the one that will allow us to make big progress. Now we find a minimum cut between them. We split the part of U away. Then we continue again and again until the size of the supernode containing P is significantly smaller than the size it started with, so constant fraction. Yeah, so this is the algorithm, the main idea there. Now let me tell you a little bit about the approximation algorithm. So our second result is as follows. Given a capacitative graph and n nodes, one can construct a 1 plus epsilon approximate flow equivalent tree in roughly n squared time. Now this is almost tight if the graph is dense, so n squared edges, and if all pairs need to be reported. Now, what would be the natural approach to construct flow equivalent tree, or to solve the all pairs max flow version for the undirected graphs? So we have actually many algorithms for many approximation algorithms for single pair max flow that run in linear time, in near linear time. So the natural approach would be to try to incorporate them as the subroutine of the Gomory-Hu algorithm that you saw earlier, and then see what happens. However, the problem is that this approach fails miserably. The error is actually unbounded, as I'll show you here. So this is an execution of the Gomory-Hu algorithm on this very simple graph. You can think about U as being infinity and epsilon as being a small constant. So initially we pick A and C as the pair. We find the minimum cut between them that is approximated. So this is going to be U plus epsilon U. This is the value. And this is instead of the minimum cut, which is U plus 1. So then we have this partial tree. Again, we have this auxiliary graph. We pick A and B. 1 plus epsilon U is the minimum cut between them in this auxiliary graph. We already see that this is much bigger than the original value between A and B, which was 2. Then we continue here. We pick C and D. Find the minimum cut between them in the auxiliary graph. 1 plus epsilon U. Then we have the final tree. Now in this final tree, you see that the minimum cut between A and B is 1 plus epsilon U, which is much bigger than 2. And so this approach fails miserably. The second issue is that cuts cross each other in the approximation setting. We cannot allow ourselves to perturb the edge weights to get unique cuts. And the reason is that the edge perturbation adds a little bit to every a little bit of capacity to every edge. This capacity that we add in the perturbation could be much smaller than the approximation factor. So we cannot allow ourselves to do that and use the similar ideas to what we saw before. So the way we overcome those issues is by a randomized algorithm that uses random pivots. And this can be looked at as mimicking the perturbation. So starting with many cuts, we'll have fewer cuts. In more detail, let's first observe something. So if we have 3 nodes, U, V, and W, the observation is that if we consider the exact minimum cut values between them, there could be either 1 or 2 distinct values, and the smallest value appears at least twice. And this follows because the minimum of the minimum cuts must separate 2 pairs of these 3. So let's say we have U, V, and W, and let's say that the minimum cut between V and W is the minimum out of the 3. And without loss of generality, assume that the minimum cut has the U in the side of V. So it must be that the minimum cut between U and W equals this value, right? These two are the same, and this one can be bigger. So if we knew the higher two of the three, we would also know the third one immediately. More specifically, if we have some pivot P, and we have that the minimum cut between P and U is different than the minimum cut between P and V, then we have the minimum cut between U and V, and it is the minimum out of these two values. And this informs our algorithm. So first we pick a pivot node uniformly at random. We have the same guarantees as before. And then we find approximate minimum PU cuts to every node U. And then we continue recursively according to the found cuts. So that if there is a cut that many nodes are associated with it, we send all of these nodes to a similar recursion set, and we deal with it later. Now, for a query pair, UV, if the cut to U is different than the cut to V, we answer the minimum between them, and otherwise we go to a deeper level that does separate them, and then we answer the minimum over there. Now, this attempt actually does not work, and let's see why. So the first case is that the value of the approximated cut between P and U is very much different than the value to V. In this case, we know that their exact values, so the values of the exact minimum cut are different. And so we also know that the value of the minimum cut between U and V is the minimum out of the exact values of the minimum cut between P and U and P and V. So they approximated, the minimum of the approximate values also approximated the minimum UV cut, and we would answer it correctly. However, if U and V had values that are close to each other, closer than the approximated ratio, then it is possible that their max flow value is very big, but we anyway send them to different recursion sets. And the reason we did that was that we had different cut to U and different cut to V. So we send them to different recursion sets just based on their cuts, and we didn't have any witness that they have small value to their cut. So the way to solve this is to reassign nodes to the found cut, so that if the maximum flow between U and V is big, and so we don't have any witness that it is small, then they would be sent to the same recursion set. The only way that we would send them to different recursion sets is if there is some evidence in the form of a cut of small value that they have small value. So in a very subtle process, we define a reassignment function that satisfies precisely that. Now the open questions are, first, is it possible to find a cut equivalent tree of a given graph in subcubic time, or even just slightly less than n applications of maximum flow? Second question is whether we can prove any conditional lower bounds for the construction of cut equivalent trees. So with that, thank you very much.